We often call Earth the blue planet because of its vast oceans of water, which are pretty rare, but our preoccupation with water misses something important. Earth isn't the only watery planet in the known universe, but it is the only fiery planet. I will prove my point as this video is about it, but before that please subscribe to my channel if you haven't already yet. In the counter of my last statement, you might be saying, wait a second, what about all the lightning and volcanoes in our solar system? Yeah, that turns out none of those things are actually fire. The sun is a huge ball of mostly hydrogen in the gas and plasma states of matter undergoing nuclear fusion, and while volcanoes spew molten rock, magma isn't on fire either, and lightning is an electrical discharge, also not fire. Only Earth has fire. So what exactly is fire, and why is it unique to Earth? Well, to get to fire it took billions of years of photosynthesis, which means fire can't exist without life, and fire and life have been shaping each other ever since today. The main oxygen gas in the atmosphere is dioxygen, or two oxygen molecules bonded together, which we usually call O2. That's what we breathe every second, but before Earth's early photosynthesizers hit the scene, we didn't have a lot of O2 in the atmosphere. Instead, the air was a spicy stew of methane, water vapor, and carbon dioxide during the initial evolution of life. The emergence of fire, a billion years of cyanobacteria photosynthesizing in the ocean, had to forge a huge amount of dioxygen that would eventually make the planet not only habitable for life but also for fire. The blip on the planet's timeline when this transformation happened is called the Great Oxygenation event, and it's the reason we're here today. The oxygen almost killed everything at first. All the excess O2 was absorbed by iron in the Earth's crust. That's why a billion years of photosynthesis had to happen. It had to overcome this sink before it could build up a reservoir in the atmosphere. We know this because as dioxygen was created by the first photosynthesizers, it reacted with iron in the Earth's crust to form iron oxide, better known as rust, and sank to the bottom of the ocean. There it formed a geologic record. We can see these records called banded iron formations in places like Western Australia and Montana, where they've been pushed up to the surface of the Earth eventually after almost 2 billion years of photosynthesis. A nice thick layer of oxygen formed in the atmosphere, but everything still lived in water. There were no forests or any plants at all on land. Now fire is the product of combustion, which is a specific chemical reaction. It needs two ingredients, fuel and dioxygen. When things get hot enough, combustion combines these two ingredients and releases water vapor and carbon dioxide. When combustion happens, the flames you see are gases emitting light, and we call it fire. Now we know what fire is and what is its phenomenon. Now we move forward, but before that please hit the subscribe button if you haven't pressed that button of glory of light and fire. So, fire needs fuel, and not just anything can be fuel. This is because combustion breaks apart the atoms and molecules of fuel and reattaches them to oxygen atoms, creating new molecules as byproducts. This process is very efficient when it has a specific type of fuel molecule, one with lots of bonds between carbon and hydrogen. The most common molecule in the bodies of plants, cellulose. Now scientists still aren't sure about what kind of plant life first took hold on land and when exactly it happened, and that's because the oldest fossil evidence of life on land, which dates to the Cambrian period about 500 million years ago, consists of microscopic spores that are hard to make inferences from, but by 430 million years ago there is a strong fossil record of life on land. There were tiny tubular filaments called neophytes, microscopic spores called paca, in the comparatively gargantuan prototaxites, which grew to about 9 m tall. It's unclear whether they photosynthesized, and they didn't have leaves, roots, or seeds. They did catch on fire. We know this because we found fossil charcoal that's that old in a very deep hole dug by the British Geological Survey back in 1978 near a small town in Wales. The researchers who discovered the oldest charcoal think that prototaxites, being the tallest thing around, probably attracted lightning, and once these early organisms were set ablaze, they became the world's first wildfires. 70 million years later, Pangea started to form, and plants spread and diversified. They ushered in a golden age of wildfire, the Carboniferous period. Now the world's first plant life didn't decompose very much when they died. Scientists think that microbial decomposers who could eat the plants hadn't evolved yet. Without a chemical or biological process that returned the bodies of the plants to the biosphere, they were buried and became part of the geosphere. After millions of years of increased temperature and pressure, they formed coal. The same coal that powered the fires of the Industrial Revolution in the Carboniferous. This surge in photosynthesis meant a surge in O2 as a byproduct. Today air is only about 21% O2, but estimates suggest that back then it was between 30 and 35%. One possible side effect of all of this extra O2 is that insects and other arthropods could get huge. For example, a dragonfly found in Britain had a 50 centimeters wingspan, and a scorpion called Puloscorpius reached almost a meter in length. More importantly, fire could get huge, though we don't know for sure. Fire with this much ambient oxygen was probably widespread, and intense flame lengths may have commonly reached over 100 meters high, and large fire whirls as well as true fire tornado may have been common also during the Carboniferous plants with true leaves, and some true wood became abundant in the fossil record. So, for the first time, fire could use leaves to travel from tree to tree. These plants were lopi trees, which could grow over 30 meters tall and had spore-bearing cones on their branches. There were also giant horsetails which had symmetrical whorls of leaves at repeated intervals. Yet by 60 million years later, in the late Permian period, many of these plants were gone out competed by trees that made seeds, but that didn't mean fire couldn't continue to thrive. Seeds are better than spores at living in dry environments, so for the first time forests existed all over the world. Charcoal in the fossil record shows that those forests carried fire with them by the late Jurassic period 150 million years ago. A family of trees you might recognize today were protecting their seeds in cones and wafting their needle leaves in the sun. These were the pines. Today, different species in the family of pines show a range of different adaptations to fire. Some have thick bark and have shed their lower branches so fire can't climb to their crowns and burn all of the living leaves. Others have adapted to be consumed by fire almost completely so their seeds can start the next generation in the nutrient-rich ashes. In 2012, researchers used DNA charcoal in the fossil record and measurements of atmospheric O2 to conclude that extra thick bark and branch shedding evolved at the same time as the strategy to be totally consumed by fire about 89 million years ago in the Cretaceous period. The amount of charcoal in the fossil record at this time suggests that there was a lot of fire, so the pines evolved two different ways to cope. But while sometimes life and evolution march along in a rhythmic progression, other times totally random events can turn everything on its head, and after millions of years of slow change, an asteroid struck the Gulf of Mexico. At the end of the Cretaceous, the impact triggered tsunami waves, earthquakes, and other mass destruction. It's even likely that at this time the whole world caught on fire. Tens of thousands of cubic kilometers of hot debris were thrown up into the air by the impact and then rained back down a layer of charcoal found in the fossil record. Covering nearly the whole planet in the aftermath of the impact suggests that entire forest must have been scoured away, but the Earth rebuilt. Over many more millions of years, and recently the most fire-loving ecosystem yet took root: grasslands. Grasses themselves had been around for 100 million years, but not long after the end of the Cretaceous period. They began forming a biome where they dominated, and by the end of the Minor Epoch around 5 million years ago, grasslands were one of the major biomes of the world. Grass keeps most of their anatomy underground, where the fire is less likely to reach it. Still, some portions of grasslands exposed to the sun seem to love to burn their above-ground tissue. Dies each fall, creating a thick thatch that new shoots and seedlings can't penetrate. Fire clears this away and returns nutrients to the soil, invigorating each season. New growth and fire kills grass's competitors, young shrubs and trees. Without repeated fires, grasslands would transform to forests, and all the millions of species that live in grasslands would be lost. Grasslands are special ecosystems with their own collection of unique animals like horses, cheetahs, prairie dogs, and flocks. Millions of migrants eating birds. Grasses include the world's most important crops like wheat, maize, and rice. Some researchers have suggested that grasslands played a role in the evolution of our Homo ancestors in Africa. Without life, fire can't exist, and in return fire has acted as a force to replenish and diversify life in almost every ecosystem. Without fire there would probably be no grasslands, and the forest of the world would likely have a lot less diversity. Earth is a water planet, sure, but even more spectacularly, Earth is the only fire planet. I hope you learned a new concept today. For other such discoveries and interesting topic, please subscribe to my channel and comment your feedback. It will help me to improve. You can also suggest new topics which you want to know about. I will research for you on it and bring an interesting video of it. Thanks for watching.